Hello, geometry students. This is Mrs. Raposa. In this geometry lesson, you'll be learning about segments and lines that are inside and outside circles and the properties of these segments and lines. So our objectives are first to identify what the names of those segments and lines are. So there's some vocabulary involved. And the second part is to use properties of these segments and lines to determine measurements. Okay, let's start with our first definition, the definition of a circle. And that's just defined as a set of points that are all the same distance away from some center point, in this case, point P. And if you see this notation right here, it looks like a circle with a dot in the center. That just stands for a circle. And in this case, it's the circle P because P is the center of the circle. So now let's talk about some of the segments that are inside circles. One of the segments is called a radius. You know what that is. A radius is a segment that starts at the center and the other endpoint is on the circle itself. And then we have something called a chord. Yeah, not that kind of chord. Okay, that's a little different one. But a chord in geometry is a segment where both endpoints are on the circle itself. So two endpoints and they're both on the circle. A diameter is a special kind of chord. It is a chord, but a better name for this segment is called a diameter because it's a chord that goes through the center of the circle. A radius, if you want to talk about multiple radiuses, we don't use that word usually. We use the word radii, plural. So PH is a radius because it has a segment and the endpoints are the center and the other endpoint is a point on the circle. And so is PD. PD is a radius of the circle and so is PF. And all radii in the same circle are going to have to be congruent because they're defined as a set of points that are all equidistant from this point P. So all of the radii in the circle will be congruent. So let's talk about which segments are chords. Chords connect 2 points on a circle and they're going to be inside the circle. So GH is a chord, FC is a chord, segment FD is a chord, and so is segment FE. They're all chords. Segment HE is a chord, but it's not the best name to use for this segment because it goes through the center of the circle. So we call that a diameter. A diameter is a chord, but it's a special kind of chord that goes through the center of the circle. Okay, now let's talk about the types of lines that intersect circles, not segments with endpoints, but lines that go on forever. One of the types of lines we'll look at is called a secant line. It intersects the circle in 2 points and goes through the circle. Every secant line will have a chord on the line, a chord with endpoints, but the secant line goes on forever. Compare that to this tangent line, this blue tangent line right here, which intersects the circle in exactly 1 point. So it just skims the circle at this point. And that point is called the point of tangency. Okay, this is a check for understanding. Give the best description for each line or segment from this diagram using one of the vocabulary words, or it could possibly be none of these. Perhaps you should pause the video right here, come up with your answers, and restart the video again. So pause the video. And if you've restarted the video, you should have found that segment CB is a radius. Line AG intersects the circle in 2 points, so that is a secant line. Segment GE intersects the circle once, but it doesn't skim the circle, so that's not a tangent line. It's none of the things that we've discussed. Line DB skims the circle at 1 point, touches the circle or intersects the circle at 1 point right there, so that is a tangent line. Segment AB is a chord that goes through the center of the circle, so it is a diameter. And then there is segment AG that has its endpoints on the circle, so that is a chord. Okay, one of the theorems we'll be using is that if I have a tangent line to a circle which intersects a circle at one point, like this line AB, at that point of tangency, if I draw the radius from that point to the center of the circle, then this radius and this line, tangent line here, are going to always be perpendicular. They'll always form a right angle, no matter where I put that point B on the circle. The measure of angle ABC always stays 90 degrees, and that is theorem 10.1. In a plane, a line is tangent to a circle if and only if the line is perpendicular to the radius of the circle at its endpoint on the circle. Okay, so let's do some examples. And our first example is example 1 right here. And in example 1, we're asked to find if ST is tangent to circle P. We're told that PT is the radius of circle P. Well, if this is part of a tangent line, then this tangent line and the radius will be perpendicular to one another. That's what I need to find out if it's perpendicular. And if it's perpendicular, then these three segments form a right triangle, where SP, which is 37, is the hypotenuse. So let's find out, is A squared plus B squared equal to C squared? And if it is, then this is a right triangle, and those two segments are perpendicular. So A in this case is, we'll let it be 35, one of the legs, and the other leg is 12. And the hypotenuse is C, 37. So let's find out if this is true. Well, 35 squared, that's 1,225. Oops, 1,225. And 12 squared is 144. And when you square 37, you get 1,369. I need to see if that's true. When you add these two numbers together, you do get 1,369. So yes, A squared plus B squared does equal C squared. So this is a right triangle. So ST is perpendicular to TP, or PT, yep. Which means yes, ST is tangent to circle P. Okay, let's do example 2. In example 2, we have a radius and a tangent line. So in the diagram, BC is tangent to circle A at point C. So I know that this radius is going to be perpendicular to the tangent line at that point. So again, I can use Pythagorean theorem, A squared plus B squared equals C squared. But in this case, C, I'm going to call it X. It's going to be the length of this entire piece. So A squared plus B squared equals C squared. So I'll have 18 squared plus 24 squared equals my hypotenuse X squared. Well, 18 squared is 324. And 24 squared is 576, so that will give me the length of the hypotenuse squared. And when you add these together, you get 900. So 900 is equal to x squared. And to find the value of x, I'm just going to take the square root of 900, and that will give me 30. So the length of this entire hypotenuse is 30. I'll put 30 centimeters. And I know that the length from A to D is a radius, so it's the same as the length from A to C. So if A to D is 18, then to find the length from B to D, I'm just going to subtract 18 from 30. And that will give me 12 centimeters. So the length from B to D is 12 centimeters. Okay, let's take a look at the last two theorems we'll be using in this lesson. Theorem 10.4 tells me that if one chord is a perpendicular bisector of another chord, remember that means this chord bisects this segment, makes it into two congruent parts. TP is congruent to RP, and it's perpendicular to this chord TR. If that's the case, then the the chord that's the perpendicular bisector must be a diameter of the circle. And in theorem 10.5, if a diameter on a circle is perpendicular to a chord, then it bisects that chord. We'll worry about the last part in another lesson. So if this diameter is perpendicular to this chord right here, then that means that FH must be congruent to DH. And we'll use that to do the next couple of examples. Okay, so let's use the last two theorems that we looked at to do examples 3 through 5. So in example 3, we need to use the diagram of circle E to find the length of AC. Well, according to theorem 10.5, if a diameter of a circle is perpendicular to a chord, then it bisects that chord. So this diameter is perpendicular to the chord, so this chord is bisected. So using theorem 10.5, CA is bisected by the diameter BD. So that means that F to A is the same length from F to C. So if F to A is 7, then F to C is also 7. So that means that AC will be 14 in length. Okay, let's take a look now at example 4. In example 4, we want to find the value of X in the diagram below. Explain your reasoning. And again, we have something similar to what we had above. We have a diameter that is perpendicular to a chord, diameter perpendicular to a chord. So according to theorem 10.5, I know that AC is bisected by the diameter BD. So that means that segment from A to this midpoint here is the same length as from here to here. So 4x has the same length as 3x plus 7. And to solve that, I'm just going to subtract 3x from each side of the equation to get x equals 7. Okay, what I did with the last answer was I just checked to see if x was 7. So I plugged that into here. 4 times 7 is 28, and 3 times 7 plus 7 is also 28. So yes, x does equal 7, makes sense. Let's take a look at the very last example. I can see that AB is the perpendicular bisector of CD because it's perpendicular, and these two segments are congruent, so it's a perpendicular bisector. So by theorem 10.4, if a chord is a perpendicular bisector of another chord, then that first chord must be the diameter, so AB is a diameter. Okay, don't forget that there are 2 parts to the homework assignment. There's a quizzes activity, and there's this worksheet. Don't forget you can go to a Google Meet or contact your teacher if you need help.